Sorry about that glitch on the end of the last video. So, differential equations. We're actually going to do systems of differential equations, but here's a little single differential equation. dx dt is a times x. Of course, we know how to solve that, don't we? That x is just x0 e to the at. It's just a function that when you multiply by a, it gives a derivative. So that's an easy system of differential equations. But what about if x was a vector and a was a matrix? And this is quite a common form. In fact, scalar nth order differential equations can be rewritten as a system of n differential equations of first order. And so there's much more generality than you might initially think. Sometimes you can just trade off the order of the differential equation as to the size of the vector. So x dot equals ax. It's a linear system of equations. But A could be a matrix that has lots of non-zero elements, and so the rate of change of one of the variables is coupled to the values of all the other variables, and that's fairly common. So linear ODEs, so sometimes write x dot equals ax, but the general solution, we usually say x as a function of time is c a to the t, but that constant c is the same as putting t equals 0. So we can write it as x0 e to the at. The thing is, we can't do that for matrices yet because, well, we need exponentials, and we don't know how to do exponentials of matrices yet. Often you solve it by separating the variables out, which is another word for move all the dx's to one side and the dt's to the other. So dx over x is a d by dt, which doesn't mean anything until we integrate. Dx over x is a dt. Integrating that, we get log x minus log of x0, putting in the limits, is equal to a times t, starting at t equals 0, which of course is just another name for x equals x0 e to the at. So, well, unfortunately, we're not going to be able to take logs of matrices or vectors either. So we're not yet there with the matrix argument. Thing that you do get from this is that if a is positive, the solution grows, and if a is negative, the solution decays. And actually, if a is complex, it tends to go round and round somehow. So electrical circuits is obviously our biggest example. Vibrating structures, buildings, the way they respond to earthquakes. Designing vibrational modes. In fact, when I was a sixth former, I went to the factory in Oxford that made the Mini, and I mean the real Mini, the little rattly one. And they told me that they had a computer with a massive, like 16 kilobytes of RAM. And they made a matrix model of the stiffness of the body of the Mini. And the reason is, this Mini was so noisy that they didn't even fit a radio because you couldn't hear it. The damn thing was so rattly. So what they do was make a system matrix that was huge because it could fit in 16K RAM. And they worked out the eigenvectors and eigenvalues, which correspond to the vibrational frequencies and vibrational modes. And sure enough, one of them was a really big vibration that the Mini hit when it was rattling along the road. And then they tried changing their model, which is essentially some like springs and dampers joined together. And they realized if they made it a little bit stiffer here and there, it would cut out that vibrational mode. And the result of that was just a bit of stiffening on the body. And then suddenly the Mini was quiet enough to actually have a radio fitted. And I was so impressed by that. It's probably why I became a mathematician. I mean, I didn't become a car designer, but, this is real stuff that's been done for very many years. Dynamics of robots, aviation, control theory of planes and ships and drones and so on, all involve systems of differential equations. Population dynamics, predator-prey equations, mathematical biology, behavioral sciences, all of these things. Okay, so Here's a little differential equation in a vector variable x1, x2. So dx1 dt is 2x1, dx2 dt is 3x2. You say this is uncoupled because we can just solve them separately to give these separate exponentials. So that was an easy case, but the way we write this as a matrix is dx dt equals a times x1. Now a is a matrix 2, 0, 0, 3. And x is a vector function of time. And of course we haven't really done anything because it's uncoupled, but the interesting case is where these numbers are not 0. So in general, uncoupled means diagonal. This matrix was already diagonal, and so the point is we're going to try and make it diagonal. Here the matrix is diagonal. We can just solve it. So how do we do that? Well, how does diagonalizing the matrix help? Well, suppose we know that A is PD P inverse. Then if you get the differential equation x dot equals ax and multiply by P inverse on the right, then what can I say? Then A is PD P inverse by definition, and so cancelling out the P and the P inverse x dot is D P inverse x. And you can think of this as a differential equation where the variables are now P inverse of x and the matrix governing it is just diagonal. So we've decoupled it at the expense of the new variables being P inverse x. So the new variables, we'll call them y equals P inverse x, they're kind of decoupled. And then the differential equation is y dot equals dy. And these are diagonal matrix, so we can just solve the differential equation separately. And in fact, that would just be e to the eigenvalue t. When we finished, we have to go back to x, which means if we've got the y, then we multiply by p to get the x. So py is the solution x. Okay, so let's do a little example. Not quite as big as a mini, but it's still a mini example. X dot is 4, 2 minus 1, 1. And we're going to put some initial conditions at x times 0. It's 1, 0. Transpose, that means it's common. So we solve this by diagonalizing the matrix, and the solutions are e to the lambda t and lambda 1t and e to lambda 2t. Notice they're both growing, and so when we put it back together and do x is p times y, we get a mixture of these two growing exponentials. So it grows in time, it's unstable. If there's a population model, say, of two species of populations explode, and so the positive eigenvalues tend to mean growth and negative eigenvalues tend to mean decay.